All righty, good morning, everyone. So last time on Friday, we finished off by talking about mirror equation. So again, mirror equation says that, and I drew a picture over here so we know what all of these different quantities are. Says that 1 over the object distance, which again is the distance from the back of the mirror to the location of the object, plus 1 over the image distance, which is the distance from the back of the mirror to the location of the image, is then equal to 1 over the focal length, where the focal length is also the distance from the back of the mirror to the location of the focal point. So that's what we call a mirror equation. And then we also have the magnification, which says the magnification, which then is the size of the image, basically, relative to the size of the object, is then equal to the size of the image divided by the size of the object, which is equal to negative of the image distance divided by the object distance. So along with the mirror equation comes some sign rules. So let's talk about the sign rules real quick. So what this says then is sign rule number 1. The focal length is positive for concave mirrors and negative for convex mirrors. The reason it's negative for convex is that it's on the opposite side of the mirror. It's behind the mirror, so no light actually passes through it. We know that the object distance is positive as long as it's on the same side at which the light is coming from, negative if it's on the other side. Now, for now, we're going to be dealing with one object, which means this will always be positive. But when we start doing combinations of lenses and mirrors, this won't always be positive. Sometimes it will be negative. But simply all it means is, in this case, this guy is positive because the light is coming this direction. So it's on the same side at which the light is coming from. Good. Sign convention number 3 then says, the image distance is positive if it's on the same side at which the light is going to, but negative if it's on the other side. So back in this picture, this would then be a positive image distance. The reason for that is, again, the light is starting here, moving from left to right, bounces off the mirror, then goes from right to left, which means that this is on the left-hand side of the mirror. So this has to be a positive image distance. But if my image was here, for example, in that case, it's on the opposite side of which the light is going to, because once it hits and bounces in this direction, it's on the opposite side, so that would be a negative image distance. And then finally, number 4 says the magnification is positive if my image is upright and negative if it's inverted. Let's go back to my picture. This then would be a negative magnification because it is inverted. It's pointing in the opposite direction as the original object itself. So that's about it. So these are my 4 sign conventions that all go along with this particular equation here. Cool. So let's use this. Let's do one more example. And then we'll move on to a group assignment, and then we'll start talking about lenses. So this says we have an external rear view car mirror is convex, which means it has a negative focal length in this case, with a radius of curvature of 16 meters, which means that the focal length is then 8 meters. Determine the location of the image and its magnification for an object which is 10 meters from the car. Good. So let's draw our scenario here. So here's my example. So in this case, we have a convex, which means our mirror is going to do this. So here's our principal axis. So here, say, is my radius of curvature. Here is my focal point, which means this distance here is going to be my focal length. And again, what we're told is that the radius of curvature is 16 meters, which means our focal length is half of our radius of curvature, which is then going to be equal to 8 meters. So, and then it says 10 meters in front of the mirror. So somewhere out here. So this distance is 8, about 8, so 10 is going to be roughly about here. There's some sort of car here. So this is some distance of S. We're told S then is equal to 10 meters. So all we want to know in this case then is where's the image. So for say part A, we want to know where is our image located. And then part B, what's the magnification? How big does this thing look relative to the actual size of it? So these are the things that I want to know. Doesn't look like a 10. Cool. So again, let's draw a ray diagram just for funsies to get some practice doing that. So again, ray number 1 is going to be the ray that goes parallel to the principal. So here's my parallel to the principal. Hits the mirror and then wants to be reflected away from as if it came from the focal point. So this is ray number 1. So this is my first ray. Good. Ray number 2 then is going to be the one that's going to try to go through the focal point here, but it can't, so it's going to hit the mirror and then be reflected parallel into the principal. So this guy's going to come in something like this. It wants to keep going here, but it can't. So it's going to come back this way. Good. So this is ray number 2. Again, our eye is going to be somewhere out here looking at this. So again, what it wants to do is see these 2 diverging rays and wants to ray trace them both backwards, meaning that this one is going to be ray traced in this direction. This one's going to be ray traced in this direction. And again, where these 2 overlap with each other, this is my image distance. So this guy here should be my S prime. So a little bit ahead of the focal points. So good. So from here, all we have to do then is, for part A, let's use our lens equation or our mirror equation, which says then that 1 over the image distance plus 1 over the object distance is equal to -1 over the focal length. So in this case, I'm inserting the negative myself to use that this focal length is positive, so that way the negative sign takes care of the fact that it has to be negative. Or you can put the negative in with the 8. It doesn't really matter how you want to do it, but I like to control my negative signs. Anal retentive. It's basically okay. So from here, all I want to do is then solve for S. So in this case, I'm gonna, or sorry, S prime. So let's subtract 1 over S from both sides. So I get 1 over S prime then is equal to -1 over F plus 1 over S. If I put a parenthesis around that, because they're both going to be negatives. From here, since I have to invert, let's find a common denominator, which is simply then going to be the product of these 2. So this is going to be the same thing then as negative. And then I'm going to get an S plus F divided by an S times F. And then finally, to find S, all I want to do is invert both sides. So this then tells me that S prime then is going to be at -S times F divided by S plus F. So it's going to be the location of my image. Let's play our numbers. So it's going to be then -10 times focal length, which is 8, divided then by 18, and this all has units of meters. Look at my numbers. What I find is, assuming I can use my calculator, which is not always true, this works out to be a -4.4 meters. Okay. Hopefully, assuming I know how to divide. Okay. What's up?
Focal length always have the radius of curvature?
Always, for spherical mediums. For spherical mediums. Okay. So finally, part B, all we want to know then is what's the magnification. So magnification then we know is equal to either the image height divided by the object height, or equal to negative of the image distance divided by the object distance. Now in this case, we don't know the original height of the objects. We don't know the image height, so we have to use the second definition. So in this case, it's going to be a negative 4.4 divided by the object distance, which is then simply 10. So this works out then to be 0.44. So this means then is that the image is 0.44 times the object height. So the image height is 0.44. So roughly about half the sum, a little bit less than that. So now in this case, the positive means that it is upright, meaning that it has exactly the same orientation, which over here is what we actually found. So again, our orientation here is it's pointing upward. Our orientation here is it's also pointing upward. So the positive just means that it has the same orientation, so it's upright. And that's it, nice and easy. So these are nice and easy expressions. It was okay? So from here, let's do a group assignment then. It'll be fun. This won't take very long. So here, all we have to do then is fill out these 2 charts. So what I have here is fill in the spaces below for the 2 different spherical mirrors. So in the first case, what I'm telling you is the type of mirror. So this is concave, which means you know the focal length is positive. So in this case, you're told the focal length, and you're also told then the object distance. From this, you want to find the radius of curvature. Well, that's just twice the size of this guy, so that's 40. So that's nice and easy. From here, you're just going to use the mirror equation. So you know the focal length, you know then the object distance, so you can easily find the image distance. And here is the magnification. R in V just means is it real or is it virtual? So how do I know it's real? How do I know it's virtual? If the image distance is positive, that means it's real. If the image distance is negative, that means it's virtual. Because for it to be negative, what it means is it has to be on the back side of the mirror, which is where no light actually goes to. So that means it has to be virtual. So if this guy is positive, this is real. If this guy is negative, this guy is virtual. And then this one is it inverted or is it upright? So you base that off of the magnification. Again, if magnification is positive, it's upright. If it's negative, it's inverted. Nice and easy. The second one, then, you're not told the type of mirror, but you all told the radius. And from the radius, you can then get the focal length. And as long as you know the focal length, you know what type of mirror it is. So in this case, since the radius is negative, that means the focal length is negative. And which of the two mirrors has a negative focal length? Convex. So automatically you know it's convex mirror. You also know the image distance. Since you already know the focal length, you know the image distance. You can then find the object distance, and then rinse and repeat for the rest of it. So nice and easy. So most of it's actually already done. I'll let you guys work on that. Won't take very long. Maybe 5-10 minutes to kind of bust through that. Start talking about some lenses.
But it's not saying that or that.
Oh, so it means is it real or is it virtual or is it inverted or is it upright? Okay. So magnification is positive when it's upright. Magnification is inverted. And for real and virtual, if S prime is positive, then it's real. So if S prime is negative, S prime. Okay. Okay. Or which one? The first one? Well, be careful. So here, did you use the negative 20? Oh, be careful. So we wrote down before is that was only true if this guy was a Okay. Let's see. Oh yeah, it would have to be. Oh, for the object distance? Is that what we're looking at? Yeah, no, object distance. So that would make it there, and then it's oh, okay. Yeah, it's a sign issue. The sign issue comes because this guy's negative, this guy's also negative. Subtracted the other side and then become positive. Which means that down here, one of these guys should be positive instead of negative. Well, it depends on where that positive is. So, let's see. So what I mean is, so here you have a 1 over f, right? And then you have a positive 1 over s prime. So we bring it to the other side, and that becomes 1 over f minus 1 over s prime. Good. So that's going to be the same thing then as what s prime minus f. Good. All over s prime times f. And then you curve that. So that's where it is. It's basically a sign issue. Well, that one everything was, yeah, that one is almost right. So this one should be s minus f, not f minus s. So then here, good, and then when you flip it, so s prime then is going to be so s prime minus f. Good. So now if you use all your signs, negative, negative, positive, s prime, which is negative. Okay. Yeah. Yeah, so m should be positive because s prime is negative. That's correct. So you have a negative, negative, which cancels out instead of positive, which makes that upright and virtual because s prime is negative. Correct. That was also virtual. And then from here, right, is that negative? Cancel the negative. Upright. Okay. Yeah. Everybody doing okay? You doing well? What happened? How hard is it? Got an answer? What answers? Okay. I'll give you that. Sure. All right. Just for you. Yeah,
Just general factor.
oh. Just use this.
We just your areas of all of this. So yeah, yeah.
Instead of saying, yeah, there. So which has more? 4 and 5.
Yeah, because that's what we did.
I had to change that, but.
Which makes sense.
Like we could get like our, yeah.
Terry, you got all this?
I do not, I'm sorry.
How we doing over here?
We did.
Good.
29.
Okay.
Like the legs, I think on the same side, it's like.
Right, sorry. Correct. So it's gonna be in the front side. So we have to about so here the legs come in this direction. It's the mirror bounces off and then it flips back in the opposite direction. So as long as it's on this side of the mirror, after it has reflected, then that's what it's saying. Now when we do lenses, next, that means that this side. Give us a lens, and like a pin, refract through the lens, travel scratch it. So in that case, instead of being on this side, both lenses. Yes. All right, so things would be cool. So next time we're going to start talking about is, so we've now seen how to create images from reflections. Right now we have plane mirrors as well as spherical mirrors. And one thing I'll note here is that plane mirrors are actually embedded inside of this expression. And so one thing to note here before I move on is that this also incorporates plane mirrors. And the reason it does that is because remember, plane mirrors at the radius of curvature is equal to infinity, which means that the focal length is also equal to infinity. So what happens in that case then is you simply get that 1 over the object distance plus 1 over the image distance is equal to 0 because 1 over infinity is equal to 0. Which means in this case that you get 1 over the object distance is equal to 1 over the image distance, which gives us exactly the expression that we want to equal. Right? So this actually incorporates both spherical mirrors and plane mirrors. It's already embedded inside of it, so we don't have to worry about writing down separate things for actually plane mirrors. But anyways, we've now seen how to create images from reflections. Next thing we want to look at then is how to create images from refraction. So images from refractions, which means we're going to start looking at lenses. We'll start talking about lenses. Now, in general, we have all kinds of different types of lenses. They could be all kinds of shapes, all kinds of different sizes, all kinds of different parameters. So for example, I could have something that looks like this. I can actually draw. So I could have a lens that looks like this. I could have a lens that looks like this. I could have a lens that looked like this. I could have a lens that looked like this. I could have basically all kinds of different types of lenses. Whatever it is that you can imagine, we can basically create a lens out of. But in general, what happens is we typically have one of 2 types of lenses. So even though each one of these lenses have different shapes to them, for example, this is 2 convex, this is doubly concave. This is what's known as plano, because in this case, it has a radius of curvature equal to infinity. So this would be plano, then concave. This would be a convex concave, etc. So we have all kinds of different shapes, but each one of these lenses typically acts like one of two types of lenses. So what are my two different types of lenses? So in general, our types of lenses are going to be number one, which is what's known as a converging lens. And then number two is what's known as a diverging lens. We already saw these in the lab, but again, let me just kind of remind you. So what's a converging lens? So a converging lens is if I simply took my lens and I draw my principal axis. So again, this guy here is what we call the principal axis, which again is the axis which bisects the lens in half. In this case, again, if I took light and I shine it parallel to the principal, what happens in this case then is the light is going to come in, it's going to hit the center of the lens, and then it's going to get reflected. This one's also going to hit, and then not reflected, but refracted. This one's going to come in, it's going to hit, it's going to become refracted. This one's going to come in, it's going to hit, it's going to become refracted. But all of these rays are going to be refracted to a particular point, where this particular point, again, is what we call the focal point. That's our focal point. So in this case, it takes all the light from a source on the outside, takes them, converts them to a particular point, which allows Nate to fry a ant. This is my converging lens. Diverging lens typically is going to have this type of shape to it. At least this is what we're going to draw in class when we're talking about that diverging lens. And here is my principal axis. So in this case, I'm going to take light, again, shining parallel to the principal. That's going to come in, hit the center of my lens here. This guy's going to hit and then get refracted outward. This guy's going to get refracted this way. This one's going to come in, hit here, get refracted, say something like this. This one's going to hit here, be mildly refracted. This one's going to get hit here and then kind of drastically refracted. But again, the point is, if I ray trace each one of these guys backwards, they all seem to come from a particular point, where again, that point is what's known as the focal point. So that's why it's called the diverging. And all these rays that come out on this side diverge away from each other as if they came from this point on the backside. So this is typically what a flashlight does. This is the type of lens that you put on a flashlight to spread out the light so you can actually see something more. Right. Now, for us, we're going to be paying attention to is mostly what are known as thin lenses. So let's talk about thin lenses. So what's a thin lens? What a thin lens is let's say here is my lens, bless you. What's going to happen is this thing's going to have a radius of curvature. So on this side, it has a radius of curvature. This side, it also has a radius of curvature. We'll talk about what happens if these two radii are not the same, but for now, let's pretend that the two radii are the same. So these guys are equal to each other. But this thing also has a width to it, where this width is what we're going to call some width t. So what a thin lens is that the width of this lens here is much, much less than the radius of curvature. This is what we call a thin lens. So a thin lens is one where the thickness of it, calling it t, where t is going to be much, much less than the radius of curvature. So good. So why do we care about thin lenses? We're for now going to care about thin lenses because that allow us to not worry about the index refraction. So what do I mean by that? So what I mean by that is if I was dealing with a thick lens, so for example, if I had a thick lens, what happened in this case then is, let's say I draw this nice kind of big fat thick lens here. So my big fat thick lens. Okay. So what happened is in this case, if I had light coming in parallel to the principal, this light then would hit, but then I'd have to abide by Snell's law across this boundary here, which means across this boundary, I then have to abide by Snell's law, which means on the interior, this thing is going to go at a different angle. I'm going to do something like this, where again, this is going to be my angle of incidence here. This is going to be my angle of refraction. And then when it comes out through the other side, I again have to abide by Snell's law on this side, which means whatever angle that this thing came in on this side, which again is going to be my new angle of incidence, let's call that theta 3. It's then going to be refracted on this side and do kind of something like this. Well, this is going to be my final angle of theta 4. So basically the point is, if I was using thick lenses, what would happen in this case then is I have to worry about the index refraction and how this thing actually deviates on the inside, because the light rays are going to go under different paths depending on how this thing actually hits and then moves through the inside of the lens. Okay? Now, the nice thing about the thin lenses, though, is since the thin lens is so thin, the deviation is going to be very, very minute, which means overall in the grand scheme of the path at which the light ray travels, it's basically insignificant, so we're going to ignore it. Okay, this is the reason that we're going to pay attention to thin lenses. So in this case, when we look at thin lenses, we will ignore the deviation of the light ray within the lens. Which means we're going to ignore Snell's law. So pretty much what that means then is when that light comes in and then hits, we're going to pretend is it's going to keep traveling in a straight line parallel to the principal until it hits the center line of the lens, which is the dashed line that I drew here. And then this guy is going to be refracted through the focal point. It's going to do something like this. Okay? So this is basically why we're going to pay attention to thin lenses. So thin lenses is we don't have to worry about Snell's law, so we don't have to take into account indexes or fractions and things like this. We can, and we probably will talk about that later, but for now, we're just going to pick one. So let's talk about then image formation from our different types of lenses. So image formation. So let's look at converging lenses first. So first thing we want to do is how do we draw a ray diagram for a thin lens or converging lens? So here is my converging lens. So in this case, I have actually two focal points. I have a focal point on the front side and I have a focal point on the back side. And these two are going to be equidistant away from the lens, meaning that the distance from the center of the lens to the focal point here is the same as what it is to here. And then we're going to stick in some sort of object. Let's say my object is going to be here. So what we want to know then is how do we draw our new ray diagrams? We know how to do it now for mirrors, but how do we actually do it for lenses? Well, here we're going to do the same thing. We're going to draw 2 out of 3 possible principal rays. So what are my 3 principal rays? So principal ray number 1 is going to be similar as before. I draw my bisecting line. So it's going to go parallel to the principal axis, hit the center of the lens, and then be refracted down through the focal point. So this is ray number 1. Ray number 2, I'll freehand it. So ray number 2 is going to be the one that's going to go, basically going to travel here to kind of try to go through, actually no, I'm going to do it on this side. So it's going to go through here, this close end focal point, until eventually hits then the lens and then go parallel to the principal one on this side. Let's do it this way. So this guy's going to come down through here, hit the lens, and then gets refracted parallel to the principal. So it's principal ray then number 2. Principal ray then number 3 is going to be the one that comes down this way, passes through the center of the lens, but doesn't get deviated in path at all. So it's going to continue moving on its merry way. So this one's going to come something like this, hit the center of the lens, and then whoops, I can't draw. There we go. That's it. So this is then principal ray number 3. There we go. Now, as before, when we talk about mirrors, what's true then is where all 3 of these rays align themselves, or at least where 2 of them align, if we only draw 2 of them, is then the location of the image. So this is my image location. This is my image. Now, let's make some notes about this image. So this image, first of all, is inverted. So this is an inverted image. And this is a real image. So again, how do I know it's real? Well, this is real because, again, the light is starting off here. It's moving to the right. refracts through the lens and continues to move to the right, which means the light keeps moving in this direction. So if I put my piece of paper here at this particular location, the image itself would be formed directly on the piece of paper. So the light is actually passing through the piece of paper. So in this case, this is what makes it a real image. This is a real image. Other things, let's get notation out of the way. This distance from the center of the lens to the location of the object is what we call the object distance. This distance from the center of the lens to the location of the image is called the image distance. And again, the distance from the center of the lens to the focal point is what we call the focal length. This is my image distance, my object distance, this is my focal length. So these are my converging lenses. Not too bad. So how do diverging lenses work then? So let's now look at a divergent lens. So here's my diverging lens. Here then is my principal axis. Again, here are my two focal points. I got one on this side and then one on this side. And again, all we're going to do is throw in some sort of object. There is my object. So what are my principal rays in this case? So my first principal ray is going to be the one that comes in again to the lens, hits the bisecting line here through the center, but then gets refracted as if it came from the focal point on the near side. So this is principal ray number one. So this thing comes in, gets diverted outward after refraction, but it comes as if it came from this particular focal point on the back side. Principal ray then number two is going to be the one that's going to try to go through this focal point on this side, but by the time it goes through the center of the lens, it's then going to get refracted, diverging away, which means it's going to run parallel to the principal. So that means that this guy here, again, as if he wants to come through here, but he can't, so he's going to go parallel to the principal, get refracted this way. This is principal ray number two. Principal ray number three then is just like last time. It's going to be the one that wants to go through the center of the lens and then get refracted, but keep going in a straight line. So it's going to do something a little bit shallow, something like this. Go out this way. This is principal ray number three. Now, again, your eye is actually sitting out here. So this is the location of my eye, looking at what's actually happening here. So what it sees then is three rays, which are all diverging away from each other. So it wants to ray trace them backwards. This one is going to ray trace along the straight line in which it actually came from. This one, it ray traces back to the focal point here. This one, it's going to ray trace backwards parallel to the principal, which means that this one is going to be ray traced back in this direction. My ray trace line, where these three ray trace lines, so ray trace number one, ray trace number two, and ray trace number three, all converge with each other, is in the location of my image. So this is my image. So just for notation purposes, again, this distance here is our object distance. This distance here from the center of the lens is my image distance. And this distance here to here is my focal length. So let's talk about this image. This image is upright. And it's upright because, again, the magnification is positive because it's in the same orientation as the original object itself. And this would be a virtual image. Again, it's virtual because if I took this guy and I put my piece of paper here, again, there's not going to be any light actually passing through this to create the actual image itself, which means if I put my piece of paper at the location at which I would see the image, there'd be no light passing through it, which means this would be a virtual image. And again, the reason for that is because the light is starting off here, going in this direction, gets refracted, and continues moving this direction to my eye, which means all the light is moving from left to right only. Nothing comes back to the left-hand side. Technically, there is some reflection, but in this case, again, if I put my piece of paper there, I get no actual image formation itself on the piece of paper. So this would be a virtual image. So these are our ray diagrams for the lenses. Now again, ray diagrams are great, but having to do them with a ruler and a protractor and all kinds of different stuff is not exactly accurate, and it's very tedious. So in this case, we can come up with a mathematical way to actually do this. Again, just like the mirror equation, this is based fully on geometry, which I'm not going to do for you like I didn't do last time, because again, I know nobody cared for the mirrors, or they're not going to care for the thin lenses. But this is what's known as a lens equation. The lens equation says that 1 over the object distance plus 1 over the image distance is equal to 1 over the focal length. And then the magnification is that the magnification is equal to the image height divided by the object height, which is equal to negative of the image distance divided by the object. Have we seen these before? Never. That's right. These are just the mirror equations. So the beautiful thing about thin lenses and mirrors is they satisfy exactly the same expressions, which means I can do multiple things with the same expressions, which means most optics is based off of 2 expressions. And that's it. So from here, again, we have sign rules. So let's talk about our sign conventions. The sign conventions are actually exactly the same thing as before, but I'm just going to rewrite them down so we know what they are. First thing is that our focal length is positive for converging lenses and negative for diverging lenses. So again, this was positive for concave mirrors and negative for convex mirrors. In this case, it's positive for converging and negative for diverging. 2, so again, the object distance is positive if on the side that the light is coming from, negative otherwise. Now, same remark as I made last time, this will pretty much always be true for a single lens, just like for a single mirror, this will always be true. But once we start combining these things together, this won't always be true. And then the image distance will be positive if on the side that light is going to, negative otherwise. And then finally, number 4, again, magnification is positive if upright and negative if inverted. So these are, again, the same sign conventions, but things are a little bit different minutely. So again, here we're talking about lenses instead of mirrors, so this is converging and diverging. The difference here is that now we have to pay a little bit more attention to where the light is coming from and going to, which means that in this case, this image distance is positive. The reason for that, again, is because the light starts here, goes through the lens and keeps moving in this direction, which means it's on the same side of which the light is going to. So the light continues to move to the right. So this would be positive, unlike mirrors, which before that was negative because it was on the opposite side of the mirror. The light actually passed through there, which means that this one now is negative because, again, in this case, light starts here, continues to move in this direction. So this would then force this to be on the side at which the light is coming from, not going to, which would then make it a negative image distance. Unlike with mirrors, where mirrors, that was where the light was going to, so that was positive. So it's a little bit switched, but otherwise, the same exact things. Was okay? Not too bad. So good. So now we know these. Let's do a couple examples just to get a little bit more comfortable with it. Combining these guys together. Good. So this says, what is the position and the size of the image of a 7.6 centimeter tall leaf placed 1 meter in front of a 50 millimeter focal length camera lens? So good. So let's draw. Now in this case, since our focal length is positive, we're going to take that then as a positive focal length, which means it's going to be a converging lens. So what's going to happen here is here's going to be my converging lens. Here's then gonna be my principal axis. Here's my focal point, here's my focal point. We're told in this case is that our focal length is equal to 50 millimeters. Now in this case, we're gonna take a height of 7.6 centimeter leaf and put that some distance. There it is. 1 meter. So our object distance is 1 meter in front. So that's 50 millimeters. 1 meter is the same thing as what, 1,000 millimeters. So that's going to be something out here-ish. Right out here. So it's going to be the location of my object. So from here, again, what I want to know is part A, what is the image distance? And then part B, what is the size? So what is my H prime? So what is my image height? Good. So again, let's just draw a ray diagram, just kind of get used to how we draw these things. So again, let me put my bisecting line in here. So again, ray number 1 is going to be the one that goes parallel to the principal. It's the center of the lens and then gets refracted down through the focal length, or the focal points. Great. Ray number 2 then is going to be the one that wants to go through the focal point on this side. Sure. It's the center of the lens and then gets refracted parallel to the principal. Like that. And then this is going to be my image. So good. So from this, what you can see is that S prime should be positive. So it should be a real image. It should be a little bit bigger than the focal length. So it should be outside the focal length, not inside the focal length. And then H prime here should be negative because it's inverted. So good. So let's work on our problem. So from here, for part A, we can then say that what 1 over the object distance plus 1 over the image distance is then equal to 1 over the focal length. In this case, our focal length is positive because our lens is a converging lens. So from this, we can find then is that our image distance is then equal to the object distance times focal length divided by the object distance minus the focal length. What are our numbers? So this is going to be what? 1,000 times 50 divided then by what? 1,000 minus 50. This is all going to have units of millimeters. From here, we find then is that S prime ends up being equal to 5.26 centimeters. I'm going to change unit systems on you. Okay. So this is my image location. So that's what, about 52.6 millimeters. Right? So again, it's a little bigger than the focal length. As we said, it should be. The light is good. Part B. We now know that the magnification is equal to the image height divided by the object height, which is then equal to negative of the image distance divided by the object distance. So from here, we can then say that our image height is then equal to negative of the image distance divided by the object distance times the object height. So this is then going to be equal to a negative, and this was equal to 52.6 millimeters divided by 50 millimeters all times H, which was 7.6 centimeters. So, pulling my numbers, what I find in this case then is this works out to be about 0.4 centimeters. That doesn't look right.
Just because you didn't millimeters off the left, centimeters off.
Man. I don't know what I did. Let's see. So 6 divided by 50, right? So that should be a little bigger than 1. Who's got a calculator?
I feel that 50 millimeters is the focal length.
Oh yeah, you're right. That's what I did. So this was divided by 1,000. Thank you. It was a good thing you showed up today. Okay, so good. So this was then equal to negative 0.4 centimeters. There we go. Good. You're absolutely right. I put in the focal length instead of the object distance. After this, I got one more for you, I think. Yeah, but we're out of time, so we'll do that Wednesday, and then we'll start talking about combinations of lenses, and then combinations of lenses with mirrors, and combinations of mirrors, and all kinds of different things. So how do we actually put all this stuff together to create interesting optical instruments? Because all optical instruments are pretty much created from combinations of all of these things. Got a haircut, Briston? Very nice.